Yeah, so I have an example here which I want to use in explaining how we choose what half reactions to use. The question is saying a startup company claims to have developed a biological process to convert methane to methanol. Calculate the methanol yield on a molar basis. So first, we want to formulate stoichiometric equation or stoichiometric equation using half reactions. The question will be, what half reactions, or how do we determine what half reactions to use? There are a number of things I want us to note before we go into selecting or how to select the half reactions. First of all, these reactions are mostly redox reactions, and in redox reaction, we need an oxidation reaction, which will be the donor. We need a reduction reaction, which will be the electroacceptor. And so both of them, reduction, oxidation, combined will give us our redox reaction. In our previous example on half reaction, I noted that the reaction that gives out the electron is the donor reaction or the oxidizing reaction. So in this reaction, the electrons will be on the right-hand side of the equation. The reaction that receives electron is the acceptor or the reduction reaction. In this reduction reaction, the electrons will be on the left-hand side. Now, the oxidized form of organic compound, particularly the carbon, is usually carbon dioxide, and in some cases, it can be carbonates or bicarbonates. Oh, sorry, there should be a negative after this. So the oxidized form of the carbon or organic compound is always carbon dioxide. In some cases, like I said, it's carbonates or bicarbonates. And then we have the reduced form of nitrogen. And usually we have nitrogen in forms of admin, and most proteinous organic compounds will contain nitrogen. And the reduced form is either ammonia, okay, ammonium here first, or ammonia. So what else? Water, okay. So in almost every half reaction, water is present either as a reactant or a product. Usually we use water in balancing for oxygen because the oxidation form of oxygen doesn't have to change, So water is used in balancing oxygen. So water can be a reactant or a product depending on what side oxygen needs to be balanced. So like I said, most reaction will contain water. Most half reactions will contain water. And then we have hydrogen ions or protons. We use this in balancing for hydrogen. So if you have your equation, you've balanced for the organic compound, the carbon, and the nitrogen, you can balance for hydrogen using protons. And then you can balance for electrons using electrons. You can balance for, the protons using, you can balance for the charges using electrons. So a proton introduces a charge into the equation, and that can be balanced up using electron. And that's why most of our half reaction, we know that we have electrons in there, which we can use to determine the electron equivalence for each organic compound. So if you observed most of, we'll go back to the main text, Rithma and McCarthy, table 2.3, you will see that most of the half reactions if you observe the half reaction, you will notice that they are composed of organic compounds, or maybe I like to say a main organic compound and the reduced or the oxidized form of some of the elements in that compound, which are then balanced with water, hydrogen, or electrons. In Rithma and McCarthy text, we know that these reactions are written. The same thing, I talked about that in the previous example, are written as reduction reactions. So because the half reactions contain one organic compound which is being oxidized or reduced, it's very easy for us to make a decision on which half reaction to use. And because most of the elements in that compound are reduced to a specific element like carbon to carbon dioxide, usually the half reactions are consistent. So if you have ethanol or methanol or methane and it's been reduced, they will all be reduced to CO2, and you can get some water or hydrogen and electrons, but just to create the balance in the equation, balance on the right and left hand side. So now let's go to the problem above. The problem we have the problem says that a company claims they can convert methane to methanol. So we know that we have an organic compound called methane, and we have another organic compound called methanol. So if we're going to select a half reaction, what we just need to do is go to our table and find methane and find methanol. So we have our half reaction equation here. We can just go through the reduced compounds. If you know the formula, you can go through this, but of course it's way easier going here. And we look for methane, and this is methane right here. And we see that methane we have the same a similar reaction. We have a similar reaction for both reactions here. So just like I'm saying, the organic compound is oxidized. So methane is oxidized to carbon dioxide, methanol is oxidized to carbon dioxide. We have hydrogen balancing the protons. We have protons balancing the hydrogen, and we have electron balancing the charge. So one positive is balanced by one negative. So very similar reactions. So we'll use these two equations, these two half reactions, in forming our stoichiometric redox equation for this problem. So the question specifically told us that this company is making methanol from methane. So we know methane is a substrate. So methane becomes the donor compound, and the reaction involving methane will be the donor reaction. Okay, so this will be our donor reaction. But if it's a donor reaction, what we state is that we switch, because all of the donor reaction is the oxidizing reaction, and we say that table 3 writes this equation as reduced in the reduction form. So what we have to do is to switch so that we have our electrons, the donor reaction, the electrons will be on the right hand side. Okay, so now we have methane is, giving out electrons, not using up electrons. It's giving out electrons. It's donating. It's a donor equation. And then we have the acceptor, methanol. So methanol is accepting electrons. Okay, so we have this compound CO2 which now accepts electrons to become methanol. So this is very straightforward. Like I said, it's very simple. In deciding what half reaction to use, you just need to know that your compound, the organic compound, and then if you know which of this compound is your substrate, you can know which of this reaction should be the oxidizing, should be changed to the oxidizing form, and which one should remain in the reduction form. So now that we have our two equations, we can just add them up like I explained in the previous example. So we know that electrons will cancel out electrons because they're on the opposite side of the equation. Hydrogen will cancel out hydrogen. There's only methane is only on one side, in only one equation and on one side. So that can come here. It's on the left hand side, so it remains on the left hand side. Methanol is also in only one of this equation, so we don't need to subtract or do anything. It will maintain its position on the side it is, which is the right hand side. So we have methanol on the right hand side. So now we have to deal with water, which is in both equation and on different sides, and we have to deal with carbon dioxide. So we know that 1/4 is greater than 1/6, so we can just move this water to the left hand side. So 1/4 moles of water minus 1/6 mole of water, and then we have carbon dioxide 2, which is 1/6 is greater than 1/8, so we can move these to the left hand side. So 1/6 minus 1/8 will be 1/24, and our water will be 1/12 moles of water. So this is our stoichiometry equation for the reaction, the conversion of methane to methanol. The question says calculate methanol yield on molar basis, which means how many moles of methanol can we get per mole of methane. So the yield will be what can you get, what product, how much of that product can you get based on the substrate. So what we did here, since they're talking about 1 mole on a molar basis, I just multiply through by 8. So 1/8 of methane times 8, 1/24 times 8, 1/12 times 8, 1/6 times 8. And so you have this equation. So you have 1 mole of methane, and then we want to find out from every 1 mole of methane, how many moles of methanol will we get. So you can break this down. This will be 4/3. So you have 4/3 moles of methanol per mole of methane, and that will give us 1.33 moles of methane per mole of 1.33 moles of methanol per mole of methane. So this is our yield on molar basis. But like I said, the main idea of this example is just to help us determine how to use determine which half reactions to use. So I'm coming back here. Suppose you want to someone wants to find out, and this is one of the examples I gave in the first video I gave on half reaction. Say ethanol production from glucose. Again, you just come here. It's so easy. You look for ethanol and glucose. You determine which is the substrate, and you can't miss it, okay? Once you know your compounds, you just go to the table, look for those compounds, and it doesn't matter if, let's say pyruvate, it doesn't matter if the equation looks scary or unreasonable to you. Once you're dealing with pyruvate conversion to, let's say, ethanol, you just pick the half reaction of pyruvate, you pick the half reaction of ethanol, and then you combine them. I hope I'm making sense. Or just randomly, if somebody wants to see citrate production from glucose, you just go to your half reaction table, you look for glucose, You look for citrate, and then you combine them. So basically, choosing a half reaction shouldn't be half reaction to use shouldn't be a big deal. It should be very straightforward. And if you're not sure if you don't find your half reaction um, in this table, you can create your own create your own half reaction by going to our main text again, Ritma and McCarthy chapter 2, which is on course site, and you go to section, I think 2.3, and you should be able to get the steps. Steps are listed on how you can create your own half reaction if that half reaction isn't here. And I guess you have one of those trials in your homework. I think you have two of such tests in your homework where you would develop the half reactions. So I hope this video has helped clarify that question on how do you determine which half reaction to use.